Hello students, let's continue class 16 on the course linear algebra and differential equation. Today we are going to see exact differential equation and the numerical solutions for a certain linear differential equation and higher order differential equation. So let's see exact differential equation. What does exact differential equation and how are we going to check whether a certain differential equation is exact or not? We have to see this. So just like from your elementary calculus course, if you remember, if we have a function phi, which is a function of two variables, x and y, then the differential or the derivative of this function of two variable phi, which is denoted by d phi, is denoted by or defined by d phi is differentiating phi with respect to x as well as with respect to y, because we have two independent variables. Yeah, so d phi is simply equal with partial of phi with respect to x times dx plus partial of phi with respect to y times dy. This is how to differentiate a function of two variables. Now, when we come to the differential equation of the form this m dx plus n dy, which is equal to 0, is said to be exact differential in a certain region R if there exists a potential function phi. This is potential function, okay, called potential function phi, such that the partial of phi, partial derivative of phi with respect to x must be this m, and partial of phi with respect to y must be this n. So we say that this differential equation is exact in a certain region if there exists what? This potential function phi, such that partial derivative of phi with respect to x must gives you this m of xy, and its derivative with respect to y must also gives us n of xy. So if this definition fulfills, we say that this differential equation is exact differential equation. A function phi that satisfies 1.94, which means this one that we have discussed recently, this definition, is called potential function. I already explained for you for the differential equation, this m dx plus n dy to mean. We emphasize that if such function exists, which means if such potential function exists, then the preceding differential equation can be written as d phi equal to 0, d phi equal to 0, because we have said that d phi is what? This d phi is equal with partial of y with respect to x times dx plus partial of phi with respect to y dy, yeah, which is equal to 0 in this case. And we have said that this is what? If there is a potential function, this is what? M of xy dx plus n of xy dy. See, this is the same. That's why if this is equal to 0, which means d phi is, this d phi must be what? Equal to 0. Therefore, the general solution to the exact differential equation m dx plus n dy is defined implicitly by what? Phi of xy equal to 0. Why is that? Because we have said that d phi is equal to 0 if the derivative of a certain potential function is 0, which means the potential function is what? Constant. Constant. That's quite true. This is true. And the proof is just easy. It's like what I have told you, because this is xy and xy dy by dx, because this was what? Dx, yeah? Upon dividing both sides by dx, this will obtain here the same. Since the differential equation is exact, there exists a potential function phi by definition, and we have that partial of y with respect to x. This was dx, yeah? Just like we divide dx to mean this is equal to 0. And of course, what we are saying is d by dx of this potential function is 0. If it is 0, which means the potential function is a constant function to mean. And this is treated as what? The general solution. This will be the general solution of the differential equation. Here we have some remarks, just like easy remarks. The potential function phi of two variables x and y, and we interpret the relationship that phi must be a constant function. And of course, geometrically, this phi of xy, which is equal to a certain constant k, or you can say it's a, no problem, is simply called the level curves, because when c varies, just it forms different with different levels, like that's why it is called level curves in mathematics. Phi of xy equal to k, where k is a constant, where k could be 0, 1, 2, 3, and so on. This forms like level curves, the level curves. So how are you going to check whether a certain differential equation is exact or not? Just simple. If we have just like this differential equation where their first partial derivative my means like partial of m with respect to y to mean, and this one n x means partial of n with respect to x, just like these are the same. Yeah? So it says m and n and their partial derivatives be continuous in a region R of xy, then the differential equation m dx plus n dy equal to 0 is exact for all xy in a certain region if this condition fulfilled. That is, if partial of m with respect to y, mind you, not with respect to x, this is with respect to y, correct, and partial of this n with respect to x, if it is equal, we say that this m dx plus n dy is exact to me. Okay, so it is easy to check whether certain differential equation is exact or not. Let's see it. Determine whether the given equation is exact or not. Let's see this. What is our m? M is here, and our n is this one, yeah? So partial m is 2x e raised y, and n is simply x squared e raised y plus cos y. So let's check. If it is exact, we have to check that partial of m with respect to y is what? This is simply the same, yeah? 2x e raised y, because this will be treated as constant. How about partial of n with respect to x? This will be what? 2x e raised y. The derivative of cos y with respect to x is 0. So as you see that partial of m with respect to y is here, and partial of n with respect to x is the same. Therefore, we can say that this differential equation is exact. That's easy. You can see. Yeah, it's exact. You can see it here. How about the second case? This one is m, and this one is minus of this one is n. And upon differentiating with respect to m with respect to y, this will be x squared only. Yes, this is x squared. And n with respect to x, that will be minus of y squared. Yeah, but they are not the same because one is positive. No. My is x squared and nx is minus y squared. So we have that x squared is different from y squared, implies not exact. Not exact. That's true. Okay, determine the general solution to this differential equation. Just like this one is a differential equation. Let's check whether it is exact or not. Here is our m, and this one is our n. So partial of m with respect to x is, with respect to y is what? That is my 1 over x. Yeah, here is 1 over x. And partial of n with respect to y is like 1 over x. Yeah, that's also true. So it is exact to me. If it is exact, if the differential equation is exact, this implies it is exact. We have said that what? If it is exact, there is a potential function phi, such that partial of phi with respect to x is m. This is m. And partial of phi with respect to y is n. So this is n. You can take it from here. This is n, and this one is m. Therefore, from these two equations, we can find the general solution to it. So from the first equation, 1, 9, 10, upon integrating phi with respect to x, just we'll obtain what? Phi of xy is the same as y ln x plus some constant c. But because we are integrating with respect to x, the constant must be a function of y, phi of y like this. That's great. So similarly, if we differentiate phi with respect to x, this partial of phi with respect to y, I mean, just like we have to equate with this to me. Upon differentiating this phi with respect to y and equating with equation 1.911, we have to find just a certain differential equation like this. You can see it here. Yeah, h is arbitrary function of y, which is treated as constant. We now determine h of y because we have to determine h of y, and it says that 1.912 also satisfies equation 1.11, which means 1.912 means the one we obtained by integrating by integrating partial of 5 with respect to x, which is equal to y over x. So this equation must also satisfy 1.911. Just upon differentiating phi with respect to y, it must satisfy 1.911. So we have to make it equate or equation. So you can say that partial of phi with respect to y is ln x plus dh by dy, and upon equating with 1.911, just will obtain dh by dy, and this dh by dy is ODE, ordinary differential equation, which is easy to integrate. You can see it. You can see it upon integrating 1 plus ln y with respect to y. It is possible to obtain h as a function of y. This is easy. So this is good. Upon obtaining this, y is equal to ln y with h for as a constant h of y, we have to substitute back here to me. Yeah, instead of h of y, we are going to see we have to substitute y ln y to mean. Therefore, our potential function is easily obtained as y ln x plus y ln c, because this is h of y. And of course, combining this, because these are logarithmic, we can combine y times ln of xy. And we have said that the solution for the differential equation, which is exact differential equation, is like d of phi must be what? 0. We have said that d of phi is equal to 0. So in this case, our phi is what? Y ln xy. Y ln xy equal to 0, which means y ln xy is constant. And like this is implicit solution. Implicit solution, because here we have y, we have also y here. So this is treated as general solution for the exact differential equation given to me. Here also, like, it is possible to consider integrating factor. Previously, we have seen the importance of integrating factor. And of course, in this case also, it's possible to use the integrating factor. But like we have a good definition here, a non-zero function I is said to be integrating factor for the differential equation m dx plus n dy if the differential equation I times m plus I times n is equal to 0 to me. If this fulfills, which means I is integrating factor to me. It's easy. Here we have an example. I show that I is equal to x squared y is an integrating factor for the differential equation. What we have to do is what? I times this, which is m, plus I times this. If it is 0, we have to say that it is integrating factor to me. Just like now, multiplying the given differential equation, which is not exact, by x squared y. So upon multiplying this by x squared y, here also x squared y, you will obtain this. Now let's check if it is exact. This is our m, and this one is our n, and partial of m with respect to y is 9x squared y squared plus 10x to the power of 4y, and nx is also the same, which means like if my is equal to nx, we say that this new differential equation is exact to me. If it is exact, which means this I, which is x squared y, is considered as an integrating factor for the given differential equation. So if it is exact, the solution is easier. We have to find from these equations, from these equations, we can find what? The potential function, and this is a potential function. We know that the potential function, which is equal to C, is considered as a general solution. Another theorem that we have about a function I is an integrating factor for m dx plus n dy if and only if its solution to the partial differential equation is n times I, that is n times partial of I with respect to x minus m times partial of I with respect to y is equal to partial of m with respect to y minus partial of n with respect to x times I, that is the integrating factor. If it fulfills this if it is the solution to this partial differential equation, we can say that I is an integrating factor for the differential equation m dx plus n dy, and also if I is an integrating factor for m dx plus n dy, which means it is also a solution to this differential equation. We have two important theorems about integrating factor. Sometimes this m dx plus n dy equal to 0 could have integrating factors that depends on x and on y, provides that there exists an integrating factor that depends only on x if and only if my minus nx over n is function of x. In this case, the integrating factor, which is dependent on x, is given as ix e raised to the integration of f of x dx. And similarly, if my by nx over m is simply gives you g of y, which means the integrating factor is a function of y, and it is given as e raised to the negative, don't forget this, the negative of the integration of g of y dy to me. This is g of y, okay? Here we have. And this f of x is given from my minus nx over n to me. Then the rest procedure will be the same. Just we can strengthen the concept by taking one example. Here we have a differential equation. This one, this is our m, and this one is our n. And you can see that partial of m with respect to y is minus 2y, and partial of n with respect to x is y. So this minus 2y and the other is y, which is not the same. So this differential equation is not exact. If not exact, we have to check whether the integrating factor is function of x or y. In this case, my minus nx is n, that is minus 2y minus 2y minus 2y minus y over xy, because n is xy. Just like y values will be cancelled out and it becomes a function of x. Therefore, this the integrating factor will be dependent only on x, and this is treated as our f of x, and accordingly our integrating factor is e raised integration of f of x. This is f of x, and our f of x is minus 3 over x. That's why we have minus here, and this will be x minus x to the power of minus 3, or we can say 1 over x cubed. Now, upon multiplying I to this differential equation, which is not exact, it will be exact. And here is the exact differential equation. Once you have exact differential equation, we can find the potential function phi as usual by using the two partial derivatives. This is the potential function, and we have said that the general solution is given by equating the potential function to a certain constant c to me. Therefore, upon rearranging, you can write the general solution as y squared minus 4x equal to c1x squared 2a. So this is the general solution to me. So this is what exact differential equation mean, how to check whether a certain differential equation is exact or not, and as well as like finding the integrating factor, and using the integrating factor we can make it not exact differential equation exact, and we can obtain the potential function. Upon finding the potential function, the general solution is simply equating the potential function with the constant c, where it forms the level curves to me. Okay, this is the first part of today's video.